All right, let's use the Bronsted-Lowry definition of what an acid and base is to identify these reactants. So Bronsted-Lowry acids, they donate hydrogen ions, or you can call them protons. Bronsted-Lowry bases are the ones that accept those protons or hydrogen ions. So let's take a look at A. This is your classic Arrhenius base as well, so we know that's also your Bronsted-Lowry base, and also the most comprehensive version is your Lewis base. So this is your hydrobromic acid that's going to have that H before, look at before the arrow, and afterwards Br has lost that H. All right, so HBr is your acid. And where did that H go? Well, it ended up here, and that O had one H, gained two, so this is your base. All right, now let's go over to B. We know hydrochloric acid, HCl, is an acid, so that H is going to be lost by the chlorine. You can see it's lost it, so HCl is your acid. And where did that H go? Well, that H went over to this water molecule, acting as the Bronsted-Lowry base. All right, so you can see it has 3 afterwards, so there's your base. The second part of this question is use the Lewis definition, so let's do that. Lewis adds is accept. He didn't look at it from the perspective of these positive particles, but rather the electrons. Lewis acids accept electron pairs. So these are typically things that are cations are often Lewis acids because they're positive, that they want to gain electrons. And then Lewis bases are the electron-rich species. These are often your anions, so they will donate electron pairs. So it's going to help to draw some Lewis structures. Let's do that. All right, potassium hydroxide. Potassium, when it's like a neutral color here. All right, potassium has no valence electrons once it loses its single valence electron to the hydroxide anion. So let me do that. So this is here your hydroxide anion. It has that extra electron from the potassium. And that is going to meet up with HBr, which is bromine is a halogen. It's got 7 valence electron and sharing a pair there with hydrogen. Hydroxide, notice it's the anion. It's got extra electrons, and because of that, it's going to be able to donate this pair. It could be any one of those pairs. It could donate that pair of electron to this proton and form a bond. So let me make a little bit more room. All right, so that proton is going to end up there. Now we don't really use arrows to draw. We use arrows to draw the movement of electrons. So that's what is going on here. The base donate is donating this pair right up there came from both of the oxygen in this case. So this is your base. It's the hydrogen that gained it. So that's why that's the acid. Okay. This is actually, it was just a proton when it came off this. All right, when it came off that HBr, it was just a proton, a naked proton, no electrons. So it gained 2 electrons from that hydroxide. So that's why it's a Lewis acid. All right, let's go to the second example, hydrochloric acid, HCl and H2O. So we'll do the Lewis structures the same way. All right, HCl is another halogen, chlorine. So it's got 7 valence electrons, and a pair is used to bond, make that covalent bond with hydrogen. And then water, I think it was. It's the water that has a pair of electrons. Again, it's going to use a pair of electrons donated to this proton to make the hydronium ions. So it's going to look like this. Right here is the pair of electrons that was used. I guess I should have circled that one there. And then that's going to form the bond. This proton didn't come with any electrons, so that's why that's the acid from the HCl. Okay, so there's your hydronium ion, which is gained that proton, so it's positive. That hydrogen is the one that gained or accepted the pair of electrons, which came from the HCl. So that's the acid. Of according to the Lewis definition. So the most comprehensive definition is the Lewis, and then you also have the same classifications using Bronsted-Lowry, where you're just following the proton.